Welcome. Today, we'll dive into LeetCode problem number 2059, minimum operations to convert number. This problem challenges us to find the minimum steps to transform a start value into a target using a series of operations. It's a great test of logical thinking and problem solving. Let's get started. In this problem, we are tasked with converting a starting number, called start, into a target number, called goal, using a specific set of rules. You are given an array called nums, which contains distinct integers, and you are allowed to pick any number from this array to perform an operation. The operations available are addition, subtraction, and bitwise XOR. Starting with the start number, you can repeatedly apply these operations to generate new numbers, and the goal is to determine the minimum number of operations required to convert start into goal. If achieving the goal is not possible using the given rules, the function should return -1. The input consists of the list nums, the integers start and goal, and all these values follow specific constraints, such as nums having a length between 1 and 100 and all its elements being distinct. The output of the problem is a single integer. This value represents the minimum number of operations required to transform start into goal. If it is impossible to reach the goal using the allowed operations and numbers from nums, the function should return -1. Let's look at an example to understand how this works. Suppose nums is 2, 4, 12, start is 2, and goal is 12. In this case, the output is 2. Here's why: you begin with the start value of 2. First, you pick the number 4 from nums and apply the addition operator, resulting in 2 plus 4 equals 6. Next, you choose 12 from nums and apply the XOR operator. The result of 6 XOR 12 is 12. At this point, the goal has been reached, and it took a total of 2 operations. Now consider another example where nums is 1, 3, start is 6, and goal is 4. Again, the output is 2. Starting with 6, you pick 3 from nums and apply the XOR operator, resulting in 6 XOR 3 equals 5. Then, you pick 1 from nums and apply the subtraction operator, giving 5, 1 equals 4. With this, the goal is reached in 2 operations. Let's examine a scenario where it is impossible to reach the goal. If nums is 2, 8, 16, start is 0, and goal is 1, the output is -1. Starting at 0, no sequence of operations using the numbers in nums will ever yield the value 1. Hence, the function should return -1 to signify that it is not possible to convert start into goal under the given constraints. This highlights how the problem involves exploring different combinations of operations and numbers to determine if the goal can be achieved and, if so, with the fewest steps. There are several important details to keep in mind. First, if the start value is already equal to the goal, the minimum number of operations is simply 0, as no transformation is needed. Additionally, if all possible operations result in numbers outside the valid range of 0 to 1000, those results are considered invalid, and the function should return -1. The constraints ensure that all numbers in nums are distinct, so there is no need to handle duplicates. Finally, the operators follow standard precedence and behavior, so you can rely on their typical mathematical definitions. These rules and constraints are crucial for correctly solving the problem and handling edge cases effectively. To solve the problem of converting the start value to the goal value with the minimum number of operations, we first considered a brute force approach. The intuition behind this method is to try every possible combination of the 3 operations addition, subtraction, and XOR for every number in the array nums. Using recursion, we can explore all potential paths to see if the goal value can be reached. However, this approach has significant drawbacks. The time complexity is exponential because it explores all possible paths without any optimization. This means the number of recursive calls can grow rapidly, making it impractical for larger input sizes. Additionally, it doesn't reuse results or eliminate invalid paths, leading to redundant computations. As a result, while simple to conceptualize, the brute force method is not computationally feasible for this problem. A more efficient solution is to use breadth-first search, or BFS, which models the problem as a graph traversal. Think of each number as a state in the graph, and the edges between states represent applying one of the 3 operations with numbers from nums. BFS is ideal because it explores all possible states level by level, guaranteeing that the shortest path to the goal is found. To implement BFS, we start with the initial value and maintain a queue where each entry represents a state along with the number of operations performed to reach it. For every state queued, we apply the 3 operations using all numbers from nums. By keeping track of visited states, we avoid cycles and unnecessary exploration. If we reach the goal, we return the count of operations, otherwise, if the queue is exhausted, we know the goal is unreachable. The complexity is manageable, as BFS explores each state only once, making it significantly faster than brute force. This method balances efficiency and simplicity, allowing us to systematically find the shortest path while controlling memory usage. Another optimization worth considering is bidirectional BFS. Instead of exploring states only from the start, this method begins 2 simultaneous BFS traversals, one from the start and another from the goal, meeting in the middle to reduce the search space. The advantage here is that it can effectively have the search depth, potentially speeding up the process. However, for this specific problem, implementing bidirectional BFS becomes challenging due to the bitwise XOR operation. Unlike addition or subtraction, XOR lacks a straightforward reverse operation, which complicates the traversal from the goal back to the start. While theoretically promising, these implementation difficulties and the relatively small range of states make bidirectional BFS less practical than standard BFS for this problem. To summarize, this problem can be modeled as a shortest path graph traversal where each state represents a number, and the edges correspond to the 3 operations. The branching factor is 3 due to the operations, and the state space is limited to the range 0, 1000, which simplifies state management and allows for efficient pruning of invalid states. When weighing the trade-offs, brute force offers simplicity but is computationally infeasible, while bidirectional BFS introduces unnecessary complexity without significant benefits here. BFS is the clear winner, striking the optimal balance between simplicity, speed, and memory efficiency. By systematically exploring all reachable states, BFS ensures correctness and finds the minimum number of operations required to reach the goal in a practical and efficient manner. This problem asks us to convert a given start number into a goal number using the minimum number of operations. The operations allowed are adding, subtracting, or XORing the start number with elements from a provided array, nums. If achieving the goal is not possible, we return -1. To solve this problem efficiently, we use the breadth-first search algorithm, or BFS. BFS is particularly suited for this because it explores all possible states at the same level, meaning the same number of operations, before moving to deeper levels. This ensures we find the minimum number of operations to reach the goal. First, we initialize the necessary components for BFS. We use a queue to store states, where each state contains the current value and the count of operations applied so far. Additionally, we maintain a set to track visited states, preventing cycles or redundant computations. Initially, we enqueue the start value with 0 operations and mark it as visited. Then, we proceed to iterate through the queue, processing each state to explore possible next states. When processing a state, if the current value equals the goal, we know we've reached the target with the minimum number of steps, so we can immediately return the operation count. Otherwise, we apply all 3 operations addition, subtraction, and XOR for each number in the nums array. For every resulting value, we check whether it lies within the valid range of 0 to 1000, as specified by the problem constraints. If the result hasn't been visited yet, we mark it as visited and enqueue it along with the increment operation count. This ensures that all possible next states are explored systematically. If we exhaust the queue without reaching the goal, it means the goal is unreachable, and we return -1. It's also important to handle edge cases, such as when the start value is already equal to the goal. In this scenario, no operations are needed, and we can directly return 0. The use of BFS ensures that we always find the optimal solution, as it processes all possible states with k operations before moving to k+1 operations. To ensure the algorithm terminates correctly and avoids unnecessary computations, we use a visited set. This set keeps track of numbers that have already been processed, preventing us from revisiting the same state and forming cycles. Additionally, constraining the results to the range of 0 to 1000 is critical. It keeps the state space manageable and ensures that we don't perform computations on invalid or irrelevant values. The BFS approach is optimal for this problem because it guarantees the shortest path in an unweighted graph. By exploring all states level by level, it ensures that the first time we reach the goal, it's done with the minimum number of operations. To implement this algorithm, we rely on two key data structures, a queue and a set. The queue allows us to process states in the correct BFS order, level by level, while the set ensures we don't revisit states, making the algorithm efficient. Now, let's look at the pseudocode to better understand how these components interact. The pseudocode begins by checking if the start value is already equal to the goal. If so, we return 0, as no operations are needed. Next, we initialize the queue with the start value and 0 operations and add the start value to the visited set. While the queue is not empty, we dequeue the front element and process it. For each number in the nums array, we compute the results of the three operations addition, subtraction, and XOR. If any of these results match the goal, we immediately return the current step count plus 1, as we've found the shortest path. Otherwise, we check if the result is within the valid range of 0 to 1000 and whether it has been visited. If both conditions are met, we mark the result as visited and enqueue it along with the increment operation count. If the queue becomes empty without finding the goal, we return -1, indicating that the goal is unreachable. This implementation ensures correctness while maintaining efficiency. When analyzing the complexity of this algorithm, the time complexity is determined by the number of states we can generate and process. Each state can produce up to 3 new states for every number in nums, leading to a maximum of 3 times the length of nums new states per current value. Since the valid range is constrained to 0 to 1000, we process at most 1000 states. This results in a worst-case time complexity of 1000*len nums. For space complexity, the queue and visited set can each hold up to 1000 states, as we only track unique values within the valid range. Thus, the space complexity is 1000. In summary, BFS ensures that we always find the minimum number of steps to reach the goal, making it the optimal choice for this problem. By leveraging efficient data structures like queues and sets, we achieve both correctness and speed. Additionally, the algorithm gracefully handles edge cases, such as immediate success or unreachable goals, ensuring robustness in all scenarios. Here, we start by importing the Deque class from Python's collections module, which will be used to implement a breadth-first search, or BFS, algorithm. Inside the solution class, we define the minimum operations method. It takes 3 parameters, nums, which is the list of numbers we can use for our operations, start, which is our starting value, and goal, the target value we're trying to reach. We initialize a queue with a tuple containing the starting value and an initial step count of 0. This queue will help us explore all possible values we can reach from the start value. Additionally, we create a visited set to keep track of numbers we've already processed, ensuring we don't revisit the same state or enter an infinite loop. Next, we enter a while loop that continues as long as there are elements in the queue. On each iteration, we dequeue the first element and check if the current value equals the goal. If it does, we return the number of steps it took to reach the goal. If the current value is outside the valid range, which is between 0 and 1000 inclusive, or if it has already been visited, we skip further processing for that value. Otherwise, we mark it as visited by adding it to the set, and then perform the 3 operations addition, subtraction, and XOR with each number in the nums list. The results of these operations are enqueued along with an increment step count, allowing us to explore these new states in subsequent iterations. Finally, if the while loop exhausts all possibilities in the queue without finding a path to the goal, we return -1 to indicate that it is impossible to reach the target value using the given operations. This return statement ensures that our algorithm handles cases where no solution exists, providing a clear and definitive result for such scenarios. By relying on BFS, this implementation guarantees that if a solution exists, we will find it in the minimum number of operations, as BFS explores all options at the current step level before moving deeper into subsequent levels. Here, we start with the Java implementation of the solution. First, we import the necessary packages, including java.util, for data structures like queues and sets. Then, we define the class solution and the method minimum operations, which takes an array of numbers, a start value, and a goal value as inputs. To solve the problem, we use a breadth-first search approach, which is implemented using a queue. Each element in the queue is an array containing the current value and the number of steps taken to reach it. We initialize the queue with the start value in 0 steps, as we haven't performed any operations yet. Additionally, we use a hash set to keep track of visited values, ensuring that we don't revisit the same number multiple times, which could lead to unnecessary computations. Inside the while loop, we dequeue the front element to process it. If the current value matches the goal, we return the number of steps, as we've successfully converted the number. However, if the value is out of bounds or has already been visited, we simply skip further processing for that value to maintain efficiency. The first step inside the loop is to mark the current value as visited by adding it to the hash set. Next, we perform operations using each number in the input array. Specifically, we calculate the result of adding, subtracting, and XORing the current value with each number in the array. For each of these operations, we enqueue the new value along with the increment step count, allowing BFS to explore all possible transformations in subsequent iterations. This ensures that we systematically explore all paths while keeping track of the number of operations performed. If the queue is exhausted and we haven't reached the goal value, it means that it's impossible to convert the start value to the goal using the given numbers and operations. In this case, we return -1 as the result, indicating failure. This completes the implementation, which ensures an optimal solution using BFS while avoiding revisiting or exploring invalid states. We'll start with a simple example to understand the problem. The input array is nums equals 1, 3, the starting value is 2, and the goal is 5. First, we initialize our queue with the starting value in 0 steps, 2, 0. The visited set is empty at this point. Now, in the first iteration, we dequeue 2, 0 from the queue, so the current value is 2 and the number of steps is 0. Since 2 is not equal to the goal, we proceed to perform all possible operations with the elements in nums. Using the number 1, we calculate 2 plus 1 equals 3, 2 1 equals 1, and 2 caret 1 equals 3. This adds 3, 1, and 1, 1 to the queue, while skipping duplicates. Next, using the number 3, we calculate 2 plus 3 equals 5, 2 3 equals -1, and 2 caret 3 equals 1. The addition operation results in 5, which we enqueue as 5, 1, while skipping out of bounds results like -1. After this iteration, the queue contains all valid results to process next. At the end of the first iteration, the queue is 3, 1, 1, 1, 3, 1, 5, 1, 1, 1, and the visited set contains 2. In the second iteration, we dequeue 3, 1 from the queue. The current value is 3, and the number of steps is now 1. Since 3 is not equal to the goal, we perform all valid operations with nums and add the results to the queue, ensuring we avoid duplicates. The visited set is updated to include 3. Then, in the third iteration, we dequeue 5, 1. Here, the current value is 5, and the number of steps is still 1. This time, we find that 5 matches the goal. Therefore, the minimum number of steps required to reach the goal is 1, which becomes our output. Now, consider a more complex example where nums equals 2, 4, 6, the start is 3, and the goal is 10. The process begins with the queue initialized as 3, 0, and an empty visited set. In the first iteration, we dequeue 3, 0. From here, we perform operations with each number in nums. Using 2, we compute 3 plus 2 equals 5, 3 to 2 equals 1, and 3 caret 2 equals 1, adding 5, 1, and 1, 1 to the queue. Using 4, we calculate 3 plus 4 equals 7, 3 4 equals -1, out of bounds, and 3 caret 4 equals 7, adding 7, 1 to the queue. Similarly, using 6, we compute 3 plus 6 equals 9, 3 6 equals -3, out of bounds, and 3 caret 6 equals 5. After processing all operations, the queue and visited set are updated accordingly. As we continue exploring valid values in subsequent iterations, avoiding duplicates, we eventually reach the goal value of 10. The total number of steps required is 4, making this the output for this example. Finally, let's look at a scenario where the goal is not reachable. Here, nums equals 5, the starting value is 0, and the goal is 100. We initialize the queue with 0, 0, and the visited set is empty. During exploration, we do q, 0, 0, and perform operations using 5. Adding, subtracting, and XORing 5 with 0 results in values like 5, -5, and 5 again. These values are enqueued if they're within bounds and not already visited. However, as we continue exploring, the queue eventually becomes empty without ever reaching the goal value of 100. This means there is no way to convert the start value to the goal using the given operations and numbers. Therefore, the output for this case is -1, indicating that the goal is not reachable. Here, we analyze the time complexity of the solution, which is 3 to the power of m, where m represents the number of operations performed per state. Let's start with the BFS traversal. Since BFS explores all states level by level, in the worst case, it could explore up to the maximum range of valid values, which is 0 to 1000, giving us up to 1001 potential states. However, not all states will be visited because the algorithm avoids revisiting states and eliminates those that are out of bounds. Now, for each state, the algorithm performs 3 operations for every number in the nums array: addition, subtraction, and XOR. If the length of nums is n, this means up to 3 n new states can be added to the queue for processing. Considering the depth of the BFS tree, the worst case could generate up to 3 to the power of d states, where d is the number of steps required to reach the goal. Since the range of valid values is bounded between 0 and 1000, d is limited. Therefore, the overall time complexity becomes 3 to the power of m, where m is the smaller value between d and 1001, and d represents the steps needed to reach the goal. Now let's dive into the space complexity, which is also 3 to the power of m, where m is the number of operations per state. The memory usage can be broken down into 3 parts. First, we have the queue, which stores the states to be processed during BFS. The size of the queue is determined by the breadth of the BFS tree, and at most, it holds 3 to the power of m states at any given time. Second, the visited set plays a crucial role in tracking explored states to prevent revisits. At most, this set can store all valid states, which is 1001 in the worst-case scenario, corresponding to the range of valid values. Finally, the algorithm uses a small number of auxiliary variables, such as current, steps, and number, which require constant 1 space. Combining these factors, the overall space complexity is dominated by the queue in the visited set, leading to 3 to the power of m. Let's compare this BFS-based approach to a brute force method. A naive approach would try generating all possible sequences of operations until the goal is found. This method would explore an exponential number of states without any pruning, making it highly inefficient compared to the BFS approach. BFS has several advantages. It guarantees efficiency by always finding the shortest path, or the minimum number of operations, to reach the goal. The use of a visited set ensures that no state is revisited, which significantly reduces redundant computations. Additionally, the problem's constraints, with the range limited to 0, 1000, ensure that the BFS remains feasible within these bounds. Analyzing different scenarios, the best case occurs when the goal is found within a few steps, requiring exploration of only a small portion of the search space. In this case, the complexity is 3 to the power of k, where k is the number of steps to the goal. The average case involves exploring intermediate BFS levels, leading to a complexity of 3 to the power of m, where m depends on the BFS tree depth. In the worst case, where the goal is unreachable, BFS would exhaust all valid states, resulting in 3,1001. The mathematical justification for this exponential growth in states lies in the branching factor. For every operation performed on each number in the nums array, the algorithm generates 3 possible outcomes: addition, subtraction, and XOR. This branching factor of 3, combined with the depth of the BFS tree, leads to the exponential growth in states. However, BFS ensures that each state is processed only once, and the visited set prevents any duplicate work. This mechanism keeps the complexity proportional to the number of unique states reachable within the valid range of 0, 1000. By carefully pruning invalid and redundant states, the algorithm balances the exponential growth with efficient state management, making it computationally feasible. When solving this problem, there are several common mistakes to watch out for. First, overlooking edge cases can lead to incorrect results. For example, if the starting number is already equal to the goal, no operations are needed, but this can be missed. Similarly, edge cases like operations causing numbers to exceed reasonable bounds should be tested. Next, inefficient state exploration is another pitfall. Brute force or unoptimized depth-first search can waste time exploring redundant states, especially for large inputs. Breadth-first search is generally preferred for this problem, as it systematically finds the minimum operations. Another issue is ignoring cycles in the state space. Without proper tracking of visited states, the algorithm might revisit the same number repeatedly, leading to infinite loops or unnecessary computations. Using a visited set can help avoid this. Additionally, misapplying operations is a frequent source of errors. Forgetting to apply all possible operations at each step or doing them in the wrong sequence can lead to incorrect results. Lastly, not validating input constraints, such as the bounds of numbers or the problem's limitations, can cause your solution to break. Always pay close attention to the constraints outlined in the problem description. Now let's focus on key insights that are especially relevant for interviews. This problem is a classic example of using breadth-first search to solve a shortest path problem. BFS guarantees the shortest path in unweighted graphs, which is why it's often the best choice here. Be sure to explain why BFS is suitable, as interviewers may ask about your reasoning. Another important point is how you define the state. For example, the state could be the current number after applying operations. Clear and logical state representation is something interviewers value highly. Optimization is another critical topic. You'll want to discuss how your solution avoids redundant computations, such as by using a visited set to prevent revisiting states. Interviewers may also ask you to compare BFS with other approaches like DFS or bidirectional search, so be ready to explain the trade-offs. Additionally, handling constraints like value bounds or maximum operations demonstrates attention to detail, which is a key skill in interviews. For related problems, you might want to look at LeetCode 752, 127, 1091, or 322. These problems share similarities in their use of BFS or shortest path techniques, and studying them can deepen your understanding of this problem's concepts. Finally, let's explore some alternative approaches you might consider. While BFS is typically the best choice for shortest path problems, depth-first search with pruning can be an option if you prefer a recursive approach. However, DFS requires careful handling to ensure efficiency, such as using memoization to avoid redundant work. Another approach is bidirectional BFS, which explores from both the start and goal simultaneously. This can significantly reduce the search space for problems with large state spaces, although it's more complex to implement. There are also cases where greedy methods might work. For example, if the operations have a clear order of priority, a greedy solution could potentially minimize the number of steps. However, this depends entirely on the problem's specific constraints and structure, so you'll need to analyze carefully to determine if a greedy approach is feasible. Each of these methods has its strengths and weaknesses, and understanding when to apply them is an important skill for tackling variations of this problem. Great job! We've covered the key concepts and techniques for solving problem number 2059, and you've learned how BFS can be applied to find minimum steps. Remember to think critically about constraints and data structures when solving similar problems. Thank you for watching, and see you in the next lesson. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!